So I'm good to go, yeah?
Yes.
Okay, so good afternoon or good morning, everybody, depending on what part of the world you're in. My name is Brendan Tierney, and what I'm going to walk through over the next kind of quarters of an hour is the new machine learning features in the Oracle database. So when I talk about the new features, it kind of depends on what you class as the new version of the database. If we look at kind of version 19 of the database, which is kind of the current kind of production version of it, is that version 12 or version 18, version 19? It's kind of, they are kind of very, very similar, but there has been a few new iterations through each version of all of those. And I'm also going to go through some of the new features in 20C, and I'll kind of come back to kind of a little bit of a caveat around all of that in a moment. So it's just, yeah, machine learning. I've written a few books on it. I'm from Ireland. I've been doing this for quite a while, and kind of I'm coming up to the 27th anniversary of my very first machine learning project, but it wasn't actually called that back then. So just maybe I'm showing my age when it comes to all of that. So you can get me on Twitter. You can find me on the blog as well. So Oralytics. And in the times that we're in it, like we're all doing our bit with social distancing or physical distancing at the moment, with this webinar. So kind of well done to the organizers for setting this up and, quite quickly and being able to kind of engage with the community on a continual basis. So what I'm going to quickly go through is a quick recap of, what is the Oracle machine learning and kind of some of the key aspects to it, which is not necessarily some of the aspects you'll see in most other presentations about machine learning. So I have a kind of slightly different perspective that I'm going to cover in relation to this. And then what I'm going to do is I'm going to pick out some of the kind of the key new features. Now, I'm not going to get into talking about formulas and maths and statistics around it, because in a lot of cases, well, do we really need some of that? And sometimes people get a little bit lost in the mathematics behind some of these. And it depends on your background, right? You don't necessarily need to be a PhD in statistics to be able to do an awful lot of this, right? You need to be able to kind of look on it as another API, another tool that you can actually use to help you to go around this. So I'm going to look at kind of three main new ones within kind of the 19C, 18C, 12C kind of version of the database, and you can get those on the Autonomous database. So, and as Gianni mentioned in his presentation a few minutes ago, since December, all of this is free, right? Like you no longer have to pay for it, which is a really important kind of change with using the machine learning features in the database. And then I'm going to look at a couple of the new algorithms that are coming in 20C. Now, I'm not going to cover everything that's in 20C. And the reason for that is I'm using the 20C preview cloud service in order to be able to test this out. And not everything is currently available in that. So we would have been hearing lots of different things like over the last 6 months, like since Open World, about here's all of these new features coming in 20C, but not all of them are available in the preview. So I'm only going to look at a couple of those kind of key new features on it. And then I'm just going to give you a few little kind of tips on things to look out for in relation to all of this. And kind of, if you're working in the machine learning world, it's kind of like, it's kind of actually a really cool thing to be doing, because everything you can do is wrong, right? So nothing you produce will actually be perfect, because you don't want perfection in relation to this. So this is where kind of the quote from George Box kind of comes in, as essentially all models are wrong, but some are more useful than others. So we're trying to use some of these algorithms and various different approaches to analyze data to help us to get a better insight into what is happening, to have a better understanding of what is happening, to help us to be able to do our job in a slightly better, more efficient way, without kind of getting too caught up in lots of the details on it. And this kind of leads on then to looking at this kind of like, the theorem of the no free lunch. An awful lot of what you hear about and talk about in machine learning is that you have to use algorithm, let's call it X, because it's the best. And every few months, you'll get a different algorithm that's being thrown out as being the best, as the best. Everyone has to use it. Everyone has to use it. And the reality is this idea of no free lunch is that, we can't make any assumptions about what algorithms are actually going to work for us or work for our data at this point in time. What we need to do is work out what algorithm gives us the best results at this point in time. And that requires us to try lots of different algorithms. Now, some of these algorithms can require a little bit of processing time, but some of them can actually run really, really quickly on large volumes of data. When I say really quickly, they can take a matter of seconds or just a few minutes. And even on the more complex algorithms, they can maybe just take a few minutes to run against many millions of records. Okay, and I'll give you some examples of that kind of later on. So what we need to do is, is like thinking of the term data science and look at the science aspects of it. Is science is about trying to do some experimentation, explore, find patterns, look at improvements, and trying to understand what works. And that's what we need to do, within the kind of the machine learning world. And it's, look, it's quite an easy thing to do. What we need to remember is that, although we may have worked out which algorithm works for my data now, it won't work or won't necessarily work forever, right? So when we go to update the models in order to capture new data, new events, and new behaviors, is we need to go through kind of the no free lunch kind of process of trying to work out which algorithm actually works best on our data now compared to a few months ago. And as part of that, it helps us to get better insights and understanding of maybe what's happening in our data and the patterns within our data. And it's kind of like, it's differences like, if we're driving a car, is like, do I really need to know all the mathematics behind the design of the engine and how it actually all works? And then, the whole engineering that goes on underneath the hood? Or do I just sit in my car and it's, I have a series of controls, a series of like APIs that I can use to perform a particular business function to get me from A to B. Do I need to get there really fast, or just do I need to be able to get there within a reasonable amount of time? Do I need to look at the safety aspects of it? Does it really matter how cool or how expensive of a car it really is, or do I need to go for cheap and cheerful and it actually does the job quite well? So in the same kind of aspects of it is that if we look on kind of the left-hand side of the screen where we have the formulas and the kind of the architecture and the design of all of these algorithms, that's like, the pure machine learning engineers, and they're trying to focus in on those algorithms. When we kind of look at applying it to business scenarios, we're more like we're the driver in the car. We want to be able to achieve certain business value for our organization. And that's what a lot of us, would kind of working in this kind of area is focusing on doing. Now, when I start looking at and kind of like Googling, saying, what are the top algorithms to use, because I have to be using the top algorithms, is that, well, here's one from a well-known kind of data science website called KD Nuggets, and kind of lists out all the different algorithms that are available or most typically available. And then you'll see is like, they're comparing 2017 versus 2019. So, and some of this kind of becomes a little bit of, whether there are trends, people become trendy or what people are really talking about. But some of it is also people are discovering that, well, as we have newer algorithms becoming available, we're finding out where they are, better used, or where they can be used, in a much better way. So it's similarly like, if we look at support vector machines, down at the bottom of the list, it was kind of quite popular back in 2017 versus 2019. And if we go up through the list, now if we take this list of, I think it's about 15 or 17 different algorithms, is that the most popular ones is that, well, they're all available within the database. So this is kind of looking at all the different algorithms within the database. So all the most popular ones that are there. Now, I need to kind of point out is kind of, if we think about deep learning in relation to audio and picture and video type analysis, that's not really what the machine learning algorithms in the database is designed for. They're designed for processing your business data. Okay, so, and these have been around, or most of them have been around for the last kind of few versions of the database, but we would have seen that the very first algorithms being available in the database were in 9i, which came out around, was it 2001 kind of time frame maybe? So that's a long time ago. So this isn't necessarily new technology, new features on it. This is well proven algorithms that have been around for 30, 40 years. But now what we have is the ability to use them in problems and a better understanding of how they can be applied, plus also the computing power compared to 30 years ago or 20 years ago is a lot better, and we can actually do this in a reasonable amount of time. Now, when we start looking at the autonomous database versus the kind of the standalone database, so to speak, like say 19C or 20C versus the autonomous, is that what we'll find is that some of the algorithms will start off in the main version of the database and then get migrated into the autonomous database. So the ones that I'm going to be looking at today are highlighted there in red. So we're going to be looking at random forest, neural network. We're going to be looking at kind of time series forecasting, which is kind of under the label of say 19C, and then we're going to go into the 20C. We're going to look at XGBoost and the Mset. Now, I'm not going to show you any algorithms because does it really matter? Here's a tool that I want to be able to go and use. It's like, do I understand the formula and algorithms behind a simple say standard deviation function? Is if you look back to your stats classes, is that, oh, maybe I did once upon a time, but you don't necessarily use that formula now. It's a formula, or it's a function call that you use. You know what to use it for. You know what goes into it. You know what kind of comes out of it, and you try to apply things from there. Okay, so what we need to do now is maybe start having a look at some of these particular algorithms. So the first I'm going to look at is to do with random forest, or sometimes it gets labeled as random forest. And you'll see the reason for some of that in a moment. And what it's based on, it's based on using decision trees. Here's a very simple decision tree, whether we use duct tape or WD-40 to loosen something. Does it move? No. Should it? Yes. Well, we need to use some WD-40 in order to loosen it up and be able to move it around. And what this gives us is something that's, that's simple, it's easy to understand, it's easy to explain, everyone can follow it. And, in reality is it can be transformed into simple if-then statements. So it's easy to code up, or being able to work with, and it's easy to understand. It's easy to extract those rules. So if you're kind of worried about GDPR, is we can extract these and being able to have explainability for all our models. On the other hand, is that it does have some kind of disadvantages. It can, it isn't necessarily the most accurate algorithm in the world. It's extremely quick to produce, and it's probably one of the quickest ones to do because the mathematics behind it, like you say, using the Gini index or information gain, is that they're very simple calculations, and is really just doing kind of counting numbers behind the scenes, being able to do those calculations. But it kind of assumes certain kind of independent variables and things like that. So we need to kind of work away from that. And one of the ways that they've come up with, or kind of one of the algorithms, is random forest or random forest, is to do with an ensemble type approach. Because if we take the decision trees, that is one particular way. That's one particular way to do it, right? And what you're relying on is the algorithms will have produced the most accurate way of doing it. Now, when we start doing this, you kind of know there's maybe one of them isn't necessarily the most efficient way of doing it. So with random forest, the idea is that it's going to create lots of different decision trees. So, on the same data set. And by doing this, we can find out multiple different ways of coming to the endpoint, or coming to the decision point of, say, doing a classification. Is someone a good customer or not? Are they potential fraudulent transaction or not? But how does it go about creating these? Now, one of the things is, like, say, you as a developer and user, is you won't be writing this algorithm. You're just going to be using this algorithm. And I'll show you how you can do that in a moment. But having a little bit of an understanding of kind of what goes on under the hood gives us a bit more appreciation of what it does. So effectively what it does, it takes different samples of the attributes and different subsets of the records. So it does some sampling on the data, it does some sampling on the attributes, and then creates a decision tree on it. And what it'll effectively do, it'll do that lots and lots and lots of different times. So what we have is then, different ways of being able to come up with a potential outcome, or being able to predict the outcome. So when we come along and say is for a new particular record, a new particular value, is that we can use these random forests, and using this idea of kind of wisdom of crowds, is that, it's like, Who Wants to Be a Millionaire, or whatever these different kind of game shows of, let's ask the audience, right? If we have 100 people in the audience, is that, well, if the majority of them kind of say, this is the answer, then you have a better chance of it actually being the right answer. So this way we can get better accuracy by kind of using this wisdom of crowds. Again, using the simple mathematics of kind of if-then statements. Computers can process that extremely quickly, and being able to kind of, process that data and get it out really, really quickly. It doesn't have any, it's less kind of bias and variance compared to like just a single decision tree. We can parallelize the work and being able to do this really, really quickly. But we do need to keep in mind is that, going back to that George Box definition of all models are wrong, but some are more useful than others. Again, say in the game show, sometimes it just gets it wrong, right? But what we're trying to do is, with all of these machine learning algorithms, is try to be a bit more intelligent and smarter, and to make these predictions to be able to help us to kind of come along. But it has lots of advantages to it, and kind of one of the main ones is kind of greater accuracy on it. But we do have model interpretability. So if I asked, say, Facebook, if they displayed a particular advert to me and they said, oh, we use the random forest algorithm to predict which advert to display to you, and under EU general data protection regulations and some other regulations around the world, you can ask for kind of an explanation of, well, how did the model pick that out? So if it's a random forest, and say the random forest used 100 different trees, they'll have no way of knowing which ones actually contributed towards the advert being displayed to you. Now, as you can imagine, is because we're creating maybe 100 trees instead of one decision tree, it's going to take a little bit longer to run. Okay, now I'll give you some kind of ideas of timings in relation to this. It is going to take a little bit more time to run, because we're creating all of this, versus decision tree, which should probably be done in a fraction of a second, on even with a few 100,000 records. But what we do get is, by spending that little bit of extra time, is we do get kind of that better degree of accuracy that comes out. Now, for each of the algorithms that I'm going to go through, is I'm going to kind of show you some code that you can actually take away and be able to use yourself. And kind of over this week, I'll take all of this code and I'll put it up as a blog post, so you can actually take it away and being able to use it. So most of the examples I'm going to use is going to be based on using one particular data set. So it's a very common kind of Portuguese telemarketing data set that's available. It's available on the UCI dataset repository, so it's quite commonly used in lots of kind of machine learning and data mining type scenarios. The defaults when you go to set up an algorithm is that, well, you need to tell what algorithm you're going to use, and the second feature is this idea called, so this particular feature within the data mining machine learning features in the database. It has this kind of auto data prep. All right. So with the auto data prep, so it kind of looks at kind of missing data prep. It looks at kind of binning and normalization and various different things like that. So before, if you had to pay the license fee, having that feature was probably worth the license fee in itself, because it actually saves you, the developer, a huge amount of time. And then what we can get onto is kind of using a create table or create model. So we pass in the model name, we say we want to do, say, a classification, we pass in the data set, an identifier to target, and being able to run all of that. And when I run that, it takes, this is the default setting is for 20 trees or 20 decision trees. It takes 4.5 seconds to run. And that's on a data set of 72,000 records. Now, if I was kind of to expand that out and kind of look at, well, other trees that or other kind of size of data sets and other numbers of trees, this little table kind of shows you kind of the comparison on all of these. So even if I go up to, say, on the defaults of 20 trees and go up to 2 million records to be able to process that, hey, it just takes over a minute to run. So not a huge amount of time to be able to run all of this. How do I call it? Well, we have these kind of prediction probability functions, and there's about 15 other different statistical or SQL functions, scoring functions, being able to use that. So we just pass in the model. The star pretty much means take all the attributes that come back from the query or from the table and pass those on in and being able to produce it. So very simple to do. Now, if I wanted to come along and change some of these settings, so if I want to say, well, 20 trees is actually too much, I only want to create 10 trees. So I'll just add in that extra parameter to my settings table. I rerun the exact same code to generate the model, and say the production code, what's there in the black box, doesn't change. No changes needs to be done. So if I have this deployed in production, I can be updating the model behind the scenes, and this can be being kind of, your production code doesn't have to change whatsoever. So kind of taking the defaults in relation to this, like 20 trees, the random set of columns, it'll take 50% of the columns for each of those trees, randomly selected, and then for each of those trees, then they'll take 50% of the data, and then kind of randomly kind of split across all of those particular scenarios. So, as we update and evolve it and become a lot more accurate, then, none of this particularly changes over time. So that's an example of kind of using kind of RandomForest to be able to get it, based on the table, you see how quickly it actually runs. Now, if I was to use this against scoring real data, it's just like querying one record, right? So it's really quick on being able to pull it back. The next one I just want to go through is to do with neural networks. And we hear a lot about neural networks, particularly with image processing and audio processing and doing lots of other things, is that, well, we can actually use it on kind of like your normal kind of business data as well. And in relation to that is like, just a quick kind of recap of how it works is that, well, it's going to take all your different input attributes, it's going to apply some random weightings to it, it's then going to apply what's known as an activation function to it. It was like maybe like a zigzag function, which is effectively going to take the inputs and map it from like 0 to a 1. Right, so you're going to fall into one of those values. So it's almost creates a little kind of S kind of curve on it and trying to do those mappings. So when it does that, it doesn't just do it once. It's through this hidden layers within the neural network. It will say do this lots of different times, and you can specify what the defaults are. Right, and then we can take the outputs from all of those, and then passing it through another kind of zigzag function is we can get the output of it, which is quite straightforward on it. But there is a lot more calculations going on, a lot more work that's going on behind the scenes to be able to do it. But having one kind of layer in it is not necessarily produce the most efficient results. So where we want to get into like the deep learning is by having lots of different layers within the neural network. So this is where it actually finds the subtleties in the patterns between the different data points. So, here's an example of a 3-layer node. And part of all of this, it takes the idea of this back propagation. Now, there's lots of different types of neural networks out there. So this is the way how the one within the database actually works, is that it kind of works out, it goes through the model, and then it's going to go through another set of iterations of taking the errors, so the things that it calculated incorrectly, and seeing that if I go back through these different layers, can I actually modify the weightings to reduce the errors? So as you can imagine, it's self-learning, right? It's evolving, self-learning to try to come up with the most optimal outcome of it. And that's why you start hearing about neural networks having really kind of good accuracy, high level of accuracy and reliability on the predictions of it. All right. Well, some of the sequences has just gone wrong, so I'll just put it all out there. So if we look at the left-hand side of the screen, we'll get to see is that, again, we have the simple kind of, let's do a neural network, set the auto data preparation on, and we're going to take the default settings, right? And when we run that, now when we run that, if you look down here at the bottom of the screen, you're going to see it took 45 seconds. Nearly 10 times longer than the RandomForest took. And in this particular case, because we didn't set the number of hidden layers, the default is it only has one hidden layer and it's doing 200 iterations, right? So 200 iterations as we go through it. Now, if I was to change that and say, hey, let's only do 10 iterations, right? The time that it'll actually take will be 7 seconds in that particular scenario, right? So it reduces down considerably over that kind of period of time. So less improvements. Does that give us a more accurate algorithm? Well, that's something that maybe part of the job is try to explore all of that, being able to work out how it compares. And again, if we take how can I actually call this, is that taking the example code that I actually showed you, for the RandomForest, is that we get to have similar type code being displayed. So it just kind of simplifies it. So you see the code on the left-hand side of the screen, it's very, very similar to what I showed you before. If I look at the code in the black box, is very similar, right? And the whole idea is this is a bit boring, right? Because they've automated and made it simple for us so that we can concentrate on delivering the business value, which is the kind of like the steps that kind of come after all of this on the screen. And then here's an example of using a 3-layer node. So in the 3-layer node is that, in the first node, I'm going to have 20, or the first layer, I'm going to have 20 nodes. In the second layer, I'm going to have 10 nodes. In the third layer, I'm going to have 6 nodes. So again, I just add that in as a setting. Everything else remains the same. When I go and inspect the results out of it, we get to see we have 3 hidden layers down there. And then down here, we get to see what the different layers contain, right? And then, if I want to be able to reduce, the number of iterations, set it to being only 10, I can add that parameter in quite easily. So this is where maybe starting with the basic parameters, seeing does it give it a good result or not, and then being able to iteratively kind of go through some of the main parameters or the hyperparameters and being able to kind of tune those and modify those so that we can end up by seeing that whether we get kind of the optimal outcome from all of this. So in a way is we need to kind of be careful of weighing this up. Now what we've seen is, if I kind of go back, is that the timing in relation to all of this. So the time that I have up here, again going for the different sets, data set size, those are in minutes and not in seconds. So the previous numbers I gave were in seconds. These are in minutes. So it does take considerably longer. So when we're getting up to like processing 2 million records, yeah, it's going to take over an hour to do. All right. But what we do get is a much deeper algorithm that has much greater accuracy and better results for us. So this is where kind of the seesaw of, are we really focused on getting the ultimate accuracy, or do we want something that kind of gives us, it's good enough, right? But it can be done a lot quicker. If we get it done a lot quicker, can we actually deploy it into production a lot quicker and get quicker results on it? Does it save us more time? Or do I spend that extra time getting the more accurate model and then deploy that? Is, that's kind of it's a bit of a seesaw. You need to kind of weigh up the kind of the costs and benefits of doing all of that. Kind of one of the features, the newer features, is time series forecasting. And this is something I think that has been really missing for quite a while, and it's kind of about time it's been there. And if we kind of think of more recent times, we've seen lots of forecasting being done, and a lot of it is kind of sticking the finger in the air and kind of just, yeah, is it going to be rain today or not, or whatever else? And just like here with the stone, does it move? Is it wet? Is it dry? We can kind of, we can do some predictions based on that. They're not necessarily very accurate, but it gives us a pointer for what we need to do or being able to look at and what we can look forward to. But with kind of looking at things beyond kind of some basic type predictions, when we start looking at, say, financial predictions or trading predictions, and again in more recent times, some of those are very, very difficult to predict, is that under normal kind of scenarios is that we have a few different situations that we need to look at. Is that is there seasonality in our data? Is there cycles in our data? Is there certain trends, or is it just kind of irregular type patterns that we might have? And what we see here in the diagrams is we see some examples relating to that. So what I'm going to do is I'm going to go through, here's some data coming from Kaggle, and it's to do with retail store kind of forecasting of it. Now, when we start doing this kind of time series forecasting, it does require data in a particular format. So the data needs to be in kind of we need a date and we need a value. Okay, so we need a date data type and then a kind of numeric values. So what I've done here is I've just taken that data set, which is have retail sales across lots of different stores. Was it over 1,000 different stores? And I've just aggregated them up, excuse me, to being on a monthly basis. And there's just a simple chart that kind of displays all of that. Now, when we come to time series forecasting, is that there's lots of different methods available within your kind of statistics or other languages on it. And one of the main kind of algorithms or approaches being used is this idea of whole winters. And a lot of other time series forecasting is actually built on top of that and built kind of to try and replicate a lot of that. So in the time series forecasting within the database, we have different features within it to be able to look at the forecasting in slightly different ways. So I'll give you just an example of that in a moment. And then we can set kind of parameters to do with, well, do we have seasonality? So it's like sun, spring, summer, winter kind of seasonality on it. Is there certain intervals on it? Is there certain kind of periods of time or different kind of patterns in the data that we might need to look out for or be able to cater for it? Right? So there's lots we need to be able to do and explore in relation to this. And what we have is the code to be able to do it. Again, kind of using similar type code that we've seen already, is that we can say we want to set up the algorithm, which is going to be the exponential smoothing. We want to use the whole winters particular model on it, or the particular just the basic kind of flavor of it. We're going to set the interval is what is the month. So when I set up that time ID or that kind of date field, is I need to be able to tell the algorithm, is that a day, is it a month, is it a week, is it whatever it needs to be. And then what I can say is, how far do you want me, or that I want you to predict into the future? Okay, so when you take that data set, do up the pattern on it, and then predict a certain number of stages forward. So in this particular case, I wanted to predict kind of 4 stages forward. Again, using similar kind of code, is that we just kind of changed the model name, the function name, and just some of those other settings on it. It was quite simple, quite basic. And when we do that, this is the kind of graph that we actually produce out of it. So the blue line represents the original data, and the red line is the trend, is the time series that we have on it. And then what we see in it, we start seeing, well, we can actually see it is picking up some of the pattern. But when we get to the very end, so the kind of the future prediction of it, it's not necessarily very, very good. Right? So what we're going to do is we're going to extend that into including seasonality within the data. So we do have seasons between, like when we see the huge peak, that's kind of December time, and then it falls off, and then it picks up again. So when we rerun everything, so all I've done is like the bit of code that's there in the bold, I've just added that in, rerun the same code, and this is the chart that we get at the very top. All right, so this is where you can see it's picking up a bit more of the peaks and the troughs. We see that trend there. We see when the data kind of dives off around the August time, we see that kind of dives off and it's picking up the kind of the trend. And then we can see it kind of predicting into the future, right? So it gives us an indication of what might happen in the future. Now, there's lots of other kind of parameters you can go setting on it. And in ways, a lot of the code that we're actually presenting here is actually a little bit boring, right? So it's a little bit kind of, yeah, so it's a little bit boring in relation to all of that. But, but that's kind of the point, right? And that's what we want to get at, is that, we can automate this really quickly. We have nice simple code that we can actually run really quickly. And what we can do is concentrating on the results that are generating so that we can give business value. Now, with the newer features, so like that's there in the preview. So I'm only looking at the preview of the database. And again, these will be migrated into Tomlin's database, so you can go and have a look at it. Is the first one that I'm going to look at is to do with what's known as XGBoost. All right. So with XGBoost is that, well, we've already seen a decision tree, right? And it's quite simple to read and understand. We've gone and seen then RandomForest, which is about, how can we actually improve upon what decision tree does? So how can we do this really, really quickly, right? And improve the accuracy of it. Now, what we can do then is start looking at is how can we take kind of like what comes out of RandomForest and how can we actually improve the accuracy again? And this is the whole idea of boosting. And with gradient boosting, what it looks at is, well, when it's building a decision tree, it's good at predicting one particular, say, type of outcomes, and it's not so good at predicting another set of outcomes, right? So if it's classification, they're not fraudulent or they're fraudulent, and this is non-fraud, right? So it's not really good at predicting those. We get a large kind of error rate on it. So what we want to do is we want to be able to take this kind of errors that has been produced is, can I produce another machine learning model, like another decision tree, that tries to predict those better, that separates them out into better accuracy of it? And that's effectively what gradient boosting is, and with XGBoost it's like an extreme version of that, so it's kind of done on steroids kind of thing, and to be ultra kind of fast on it. All right, so this slide kind of goes around a lot of the steps I've kind of just adding on it. So what it effectively does, it kind of produces one particular model on it, looks at the errors, produces a model excuse me, based on those errors, look at how many errors do we still have, and then goes, well, can I create another model on that, another model on that, another model on, and each time it creates a new model, it's extending the original model, so it's kind of building it out, and each time it's trying to reduce the number of errors in it. So maybe after 3, 4, 5, 6 trees, it's actually working on really tiny data sets. So each iteration becomes quicker and quicker and quicker as we go through it. So there's just kind of a pictorial kind of version of the 3 different scenarios of it. Now, when we start looking at all of this, is that this is probably one of the more complex algorithms to use within the database. It's got over kind of 40 different parameters on it. It can be a bit difficult to kind of grasp all of it, and that can sometimes put off people from using it. Let's kind of take the defaults and kind of being able to kind of run in relation to that. So I've kind of given what probably the main, was it 5 main parameters that you would probably be kind of more familiar with having used the other algorithms that are there. So again, using the same kind of boring code on it is that, well, I'm going to set up the settings that will have, we're going to use the XGBoost. We're doing, say, binary logistic regression, which is just kind of binary classification on it. And then I'll generate the model. All right. So if you kind of look back to the example code that I actually did for the RandomForest, is that code is pretty much almost the same, right? The only thing different in it is the name of the settings table and the name of the model. So kind of, again, it becomes a little bit kind of boring. Now, when I run that, it's kind of, how quick is it? And you kind of go, oh, like, it's actually quicker than the RandomForest. Just on the environment that I use, which is the default settings. I didn't scale it up or anything like that. So it's the default kind of settings on it. Even for 2 million records, just took a little over a minute to be able to go run. So really, really quick and really efficient to do it. But we can start expanding some of this, is that, rather than say the default, how many layers or depth of the tree that we want to go down, instead of it being 6, I want to go shallower. I only want to go down 3 layers. If I want to look at the accuracy, I want to look at, it's the the error and the area under the curve, and the number of times I want to kind of maybe go around the process to try to do some of the improvements, or kind of the number of layers down I want to go, I'm going to reduce that from 10 to 5. So this is a way of being able to almost compact the amount of work that I want to be able to do. And when I kind of go and run all of that, as you can see now, is that the results have, kind of shrunk down quite a bit. So even like, with, was it the 660,000 data set is like 15 seconds. It's being able to kind of go and being able to run at. And part of that is to do with like, each particular iteration, or each as it builds out the decision tree, it's working on a smaller and smaller kind of different data set. Now we're kind of, have about another few minutes kind of left on it. So kind of coming up to the last algorithm that I want to show you is to do with, it's called Multivariate State Estimation Technique, or Mset, right? And this is kind of quite a, this is an algorithm that's been around for 20 years or more. And effectively what it's to do is it's looking for, or can be used for anomaly detection. So we can see some examples of anomaly detection. And the usual approach is when we go about trying to look at for anomaly detection, we can start off doing some simple descriptive analytics, into some more advanced analytics, into using some of the different machine learning algorithms. And one of the ones that we have already within the database for anomaly detection is known as a one-class support vector machine. All right, so that's one particular approach to use. So with the Mset, is that where it actually comes from is from measuring sensor data. Right? And it originally kind of came out of looking at energy generation plants, airplanes, space travel. Disney uses it, and hardware failures. So kind of have a link there at the bottom of the slide, and you'll be able to get that. It's a link to a paper that comes out of Sun Microsystems from around 2000, that talks about kind of using this, being able to look at hardware failure. So being able to look at the sensors and the signals coming out of the different hardware components, could they actually predict when the component might fail? So it's actually cheaper to, being able to see and monitor what's going on and do a scheduled downtime to replace parts, rather than the part failing and having to do emergency replacement in relation to that. So what it effectively does, it starts looking for kind of subtle kind of differences in the signals that are coming through and the values of those signals coming through versus what would be considered normal kind of patterns of it, and being able to use that. So this is kind of used quite extensively, particularly in the IoT and kind of sensor areas. But what they've been able to do is being able to bring that into the database and being able to use it on financial data and other type data. Now it is a time series type data set. So similarly, just like our previous example of doing time series, we need to have kind of data processing on it, or data label on it, and being able to kind of explain it all out. So here's some example code again. What I'm going to do is, if I just use the simple sales history scheme on it, what I'm going to do is I'm going to build up kind of a data set that has some, so based on the different days, I'm just going to aggregate some data on it. And then what I'm going to do is, again, using the settings, kind of create, to put in the defaults on it. And then what I'm going to say is, well, we want to be able to determine if a fault occurs 3 times within a window of, say, 5 events, then that's an anomaly that we need to be able to look out for. So if things go outside the norm 3 times, we want that flagged. Now, that might seem a rather small window, but in this particular example, it's perfectly fine. Then we go create the model, so it's the code on the right-hand side. Just, again, standard code that you're going to see, and then being able to go and run it and do the predictions on it. And this is what it will effectively do, is it'll look for data that has anomalies on it, and how it'll actually flag the data when it does the kind of the prediction on it. If anything that has a 0, that's considered normal behavior, right? Anything that's outside that normal behavior gets classed with a 0. Hence, we have the 0 in the where clause to only bring back those particular values. So we can use this for maybe monitoring database events, financial data, financial trading, lots of different things that are happening within our data. So is there anything else? It's kind of like, as our good friend you say, just kind of one more thing, is that, one of the ways we can speed up our models significantly is to do this idea of partitioned models. So we're partitioned models, what we're trying to do is, rather than us having the right code or partition data out into different subsets of the data, maybe for geographic region or based on certain attribute values, is, that's creating work for us, is could I not just tell the algorithm to do that for me? And the answer is, well, we can, right? So if I kind of go back to the random forest example, is that one of the things I can say is take, the marital value and say is, well, I want to create a separate machine learning model for each one of those because they behave differently, right? So if we kind of take the exact same code to generate the model that we had previously, same code if I want to use it for scoring on it, is when I run this, that what we have is 4 different values for the marital. So without having to write any extra code, is just add in the setting, is it'll actually generate 4 models for us, right? And if I compare that using just the default settings, is that the original model took, say, on 72,000 records, took 5 seconds. This time it took 8 seconds, right? So it's doing 3 extra machine learning models. And what it effectively does is this idea of a meta model that contains each of these 4 ones. So when I come along and I use like the code in the black box to score new data, it will actually look at that attribute of marital, it'll see what the value is, and then under that meta model, work out which of those 4 it needs to apply to it, right? So we get greater accuracy in our results because the models are more focused on a particular subset and particular behavior within the data. Now, one of the things I could do is I come along and say is, well, I could add extra attributes into it. So we have marital, but we also have job. So in this particular case, we have 12 different job types. So if we take the marital values by the jobs, it ends up by creating 48 different models. And in this particular case, that on the 72,000 took 34 seconds to be able to run. You might start going, oh, that's kind of getting quite big, particularly if I was to scale that out for like the 2 million data set. So one of the things I could do is I want to divide up the work on that and create a separate slave for each of those different partitions. Right? So if we're in a multi-core environment, we can actually do a lot of this in parallel. So when I actually kind of take that and divide that out in parallel and put in that, is that those 48 models, it took 6 seconds or 6.5 seconds to be able to run. Right? So by one simple parameter change, on the base image, and build of the cloud service, is that it suddenly transformed the speed of what we needed to do. So again, look out for this. We can go use it, in the database very quickly, and then improve the performance of our code. So, kind of coming towards the end, kind of just to wrap things up, is that remember, the no free lunch. We are in kind of a science explorative environment. We need to be able to work out what actually works for us. We shouldn't necessarily follow trends, and kind of quoting the Irish Prime Minister in kind of recent days, kind of the government needs to make decisions based on science rather than social media or political pressure. Is kind of like, rather than what is trendy in the press or in the marketing, is we need to be able to work out what actually works for us. When we go about working this out, is that, we do need to weigh up, the speed of creating the models versus the ease of deployment versus how much accuracy or how good the models really are. And, kind of, again, based on kind of recent times, is kind of this great Irishman from who is he's the executive director of WHO, the World Health Organization, of emergency programs, was talking about how we need to respond to current times. We need to act quickly, be fast, be the first mover. We need to do things quickly, and the quicker you are, the more benefits you're going to get. So it's kind of like what I kind of like to talk about is like, it's the 50 Shades of Grey approach. So if you're kind of the pure machine learning people, you want to get those beautiful models. You want to get the ones that are most optimized ones for your particular scenario, for your data. And that can take some time to be able to do it, right? So 50 Shades of Grey. Or you can go about the Nike approach, right? Or we can just do it. We can take something that actually works. And while people are working on the beautiful models, is that over that kind of week, 2, 3, or 4 weeks, is that we actually are deploying kind of a model that maybe is good enough and being able to get some results on it. And some of those results are going to be financial results. But some of those results is also a better understanding of what's happening on our data. And that kind of comes down to, it's like, do we wait to have the optimal type of mobile phone, or do we take something that works and constantly evolve it? And kind of like, as Stuart Bryson kind of has talked about in the past, about agile data warehouse kind of development, is that you want to have maybe the Ferrari or the Porsche at the very end, but in order to be able to get there, you might need to evolve from a Mini Cooper back to a scooter into lots of different types of vehicles before you might actually get to your optimal solution or your ideal solution. But along the way, you will have learned so much more. And by doing that, yes, there is going to be some boring stuff, but a lot of that boring stuff can be automated quite easily. We can script it up, we can make it really easy, but what we really need to do is focus in on delivering business value, right? So being able to not get too caught up in the formulas and the statistics behind all of it, is this is another tool that we can actually use to help us deliver what we want to be able to do. So that was kind of a quick run through of some of the kind of the key algorithms and that are available within the database, and some of what's kind of coming up. I showed you a couple that's available under the 12c preview. When 12c comes out, things may be different or whatever else. And then kind of finished off on, we also looked at partition models. Again, it's not necessarily something you see talked about or kind of written about or shown much, but it can give you kind of greater accuracy and can be done really, really quickly. Don't forget the no free lunch aspects of it. Try all the algorithms. It can be easy scripted up, and you can evaluate them all out of it and be quick about it, right? Go and apply it, productionalize it. Think of how you're going to productionalize it and evolve over time to giving you the most kind of optimal solution out there. I've slightly overrun on time, so thank you very much for bearing with me. Hopefully you're not all like what's in the picture. I'd like to thank all the organizers of this event. It was a great idea, and for being so quick at getting it up and running. And for everyone else, just remember, stay safe, and hopefully we'll get through all of this well. All right. And don't forget, over the next couple of days, we have Apex tomorrow and databases on Wednesday. So thank you very much. I'm going to hand back to Gianni, maybe.
Yeah, Brandon, there is a question for you. Are those all in the basic database, or do you require selecting an option or something special for the installation?
So they should be all there in the database. You don't have to do any extra install. If you were to go back to like 11 and the early days of 12, it was an extra install. Or no, I think it came as, it came as part of the base install. You actually had to turn it off if you didn't want it in the database. So whether you're using the database as a service or using the autonomous, they're going to be there.
Perfect. That was the only one left, yeah.
Okay. If there's no other questions, then thank you all very much. And it's time for Stuart.
Hello.